History and structure of the atom. Unit 2, atoms. First, let's talk about what an atom is. An atom is the smallest particle of an element that retains the chemical properties of that element. All matter is composed of atoms. So the chair that you're sitting on, your body, the clothes that you're wearing, your dog, your cat, the bed you sleep on, the house you live in, all of that is composed of atoms. And atoms are in constant motion. They're always spinning. They're never at rest. They're constantly moving. And we'll talk more about the spinning of atoms later on in another unit. It took many years for us to develop our theory on atoms, and it took many scientists as well. And this is what we're talking about today. Because atoms are so small, we're going to be using models to show their structure because we can't grab a microscope and show you an atom. As we learn more about the atom, we have to update our models of every decade or so. A new scientist comes around with theories and evidence to help improve the model structure of an atom. And as time progresses, of course, we're going to change that model depending on the research we find. This is an outline right here at the bottom, and it traces the understanding of the atom from the ancient Greeks, far on the left. Oh, actually, it's before John Dalton. It's not shown on this image. All the way to the modern model of the atom that we use today. So the first atomic thought was developed around 400 BC with Democritus. He proposed that matter was composed of tiny, indivisible particles. So small, so indivisible, not invisible, but indivisible, meaning that they cannot be broken apart. He called these atoms because in Greek, atomos means indivisible. Now, this was just a theory. It was not based on experimental data. Back then, philosophers just used to get together and think about things and give reasons for those things. Democritus was one of those philosophers. Unfortunately, Aristotle did not like Democritus' ideas. He believed, with no experimentation again, that all substances were made of the 5 elements: fire, earth, water, air, and ether. Because he didn't believe in Democritus' ideas, he misled all of his followers. He was a teacher, so he taught his ideas. He misled all of his followers to believe that everything was made up these 5 elements only. For more than 2,000 years, this is what everyone believed. And we didn't bring back atoms until the 1700s. We call John Dalton the father of the modern atomic model because he built on the ideas of Democritus. He described that atoms were tiny particles that could not be divided. So he knew Democritus was telling the truth. We weren't made of 5 elements, we were made of tiny particles. His theory of the atomic model included the law of conservation of mass, the law of definite proportions, law of multiple proportions, and the 4 postulates. So these are the 3 laws. We talked about law of conservation of mass before. In a chemical reaction, matter is neither created nor destroyed. It's just rearranged. So the particles, that he calls atoms, are just going to be rearranging with each other. They're also going to be there before and after a reaction. The law of definite proportion states that a chemical compound contains the same elements in the same proportions no matter the source or size of the sample. For example, carbon dioxide, the gas, is always going to have the same ratio of 1 carbon to 2 oxygens. It will always be like that. And then the law of multiple proportions. The same elements can combine in different proportions to form different compounds. So yes, we can combine more atoms if we need to create different things. For example, just 1 carbon and 1 oxygen makes carbon monoxide. But when we add that other oxygen, that's where we get the carbon dioxide with the 2 oxygens. Either way, in a room full of carbon monoxide, all of the atoms would have 1 carbon, 1 oxygen because of the law of definite proportions. And a room full of carbon dioxide would always have one carbon to two oxygens because of the law of definite proportions. So these are Dalton's four postulates. Elements are composed of small, indivisible particles called atoms, just like Democritus said. Atoms of the same element are identical. Atoms of different elements are different. So every gold atom is going to look like every other gold atom. But gold atoms are not going to look like aluminum atoms. Number 3, atoms of different elements combine together in simple proportions to create compounds. We talked about elements and compounds in the last unit. We talked about pure substances. And yes, we do know that atoms and elements can combine to make those compounds. And number 4, in a chemical reaction, atoms are not created, destroyed, or changed. They are only rearranged. And this was the law that followed for many, many years. In 1807, we have John Dalton, who created his billiard ball model. And this was the atom that we used again for many, many years. He said it was a solid sphere, it was indivisible, so it couldn't be cut, and it was uniformly dense and very, very tiny. In 1897, another scientist came about, J.J. Thomson. He discovered the electrons were smaller particles of an atom. So an atom wasn't just composed of one spherical ball, it was composed of tiny electrons around. He created the plum pudding model, which stated a positive sphere with negative electrons dispersed throughout. He actually calls this the plum pudding model because, well, pudding was a thing back in the day, and putting plums in it was a thing. So when he looked at this, he decided that it reminded him of plums inside of his pudding, and that's why he called it the plum pudding model. Around 1911, Ernest Rutherford knew that atoms had positive and negative particles, but could not decide how they were arranged. So he knew there wasn't just electrons, but there had to be protons somewhere. That's how he discovered the nucleus and created the nuclear model. He said that an atom was dense, contained a positive nucleus, and that nucleus was surrounded by negative electrons. Then we have Bohr. Niels Bohr came around and proposed that electrons traveled in fixed paths around the nucleus. He called these the energy levels, stating that electrons could only exist in specific energy states. Here on this example on the right, we have the nucleus. Outside of it, we have the first energy level with 2 electrons. Then we have the second energy level with 8. Then we have the third energy level. And it went on and on and on, just like that. Scientists actually still use this model to show the number of electrons in each orbit around the nucleus. We're going to actually be using this model too when we get to levels, energy levels for electrons. Niels Bohr called this the planetary model because the electrons moved in circular orbits within specific energy levels, just like planets rotated around the sun in their own rotation. Then we have Aaron Skorschendinger. He used mathematical equations to predict the locations of electrons. In this image right here on the right, these dots don't exactly represent actual electrons. They just represent the probability of where an electron can be. This is called the electron cloud model because the orbital region around the nucleus, again, wasn't like Niels Bohr. It didn't have specific paths. Instead, these electrons traveled around the nucleus in random orbits. He said that scientists cannot predict where they will be given at any moment. And this is because electrons travel so fast that they appear to form a cloud around the nucleus. And he called this the cloud of probability. Again, you could see the cloud surrounding the nucleus. And again, these are all the points where electrons could be. Then in 1932, James Chadwick said that the mass of an atom was too high to contain only protons and electrons. the weight didn't add up. So he discovered neutrons. They were the neutral part of the nucleus. They did not have a charge. And then he created the neutron model from this. It's just a revision of Rutherford's model. Here you can see that the protons and the neutrons are in the center of the nucleus, and they're surrounded by electrons on the outside. So now we're going to talk about the structure of the atom, what we have. Again, an atom is the smallest particle of an element that retains the chemical properties of that element. Atoms are always going to be made of three subatomic particles: protons, neutrons, and electrons. Protons are going to be the positive charge of the atom. Each proton has a mass of 1 AMU, which is 1 atomic mass unit, and it's found in the nucleus, which is in the center of the atom. Usually, the number of protons in an atom is going to identify what element it is. So based on the protons, we can find out what element we have. Neutrons have no charge. Each one is going to have a mass of 1 atomic mass unit, and they're also found inside the nucleus along with protons. So the amount of neutrons is going to vary depending on isotopes, but we'll talk more about ions and isotopes later on. Electrons have a negative charge, and they have very little mass. They do not weigh as much as a proton and a neutron. Electrons are found in the regions around the nucleus called orbitals. So they're not in the center, they're on the outer parts. And an atom usually has the same number of electrons as protons when we're talking about neutral atoms. Again, when we get into ions, we're going to see that there are different amounts between protons and electrons, but we won't get there yet. As of now, neutral atoms have the same number of electrons as protons. We have two regions of an atom. I've said these already: a nucleus and the electron region. The nucleus is very small, yet it makes up most of the mass of the atom because protons and neutrons both weigh a lot more than the electrons. They do contain the positive protons and the neutral neutrons, and because of that, the nucleus has an overall positive charge. Strong forces, called nuclear forces, hold the nuclear particles together. And that's why it's really hard to separate an atom, because of those nuclear forces. When we do separate atoms, that's how we create nuclear reactions, bombs essentially. The electron region is sometimes called the electron cloud because it's where electrons kind of move around about. It is a very large region compared to the nucleus. It does contain a negative charge because only electrons and empty space are in that area. But remember, it's very light because electrons have almost no mass. Before we end, I'm going to show you how to read a periodic chart because you're going to need to know this on some of the questions in today's assignment. Element names are going to be found at the bottom. These are the element's common name. And then symbols are going to be composed of 1 or 2 letters, and this is going to represent the element. The atomic number at the top is going to show the number of protons in an atom. This is going to identify the element, and it's going to tell us which element we have. Again, protons tell us which element we have. In a neutral atom, this is also going to equal the electrons. So hydrogen has 1 proton and 1 electron. Note that the periodic table is arranged according to its increasing atomic number. We're not talking about average atomic mass, which is found on the periodic chart, but we will be talking about atomic mass. So atomic mass is just the number of protons and neutrons in a single atom that we're talking about at the moment. We're not averaging up masses of multiple atoms, not yet. So the atomic mass number will always be given. You can't find it on the chart. All right, so that's it. Now complete your practice assignment on Schoology.